Hello again, folks, in 114. Today we're going to be covering section 12.5. If you noticed on the calendar, I had actually spread this over the course of 2 days. I don't think that's going to be necessary, but if you look in my lab, right, there are probably 2 parts to 12.5. I've forgotten right now, but I believe that is the case, and that was the real reason for this being like so. All right. Anyhow, today is Monday, the 19th, so we're covering section 12.5. All right. And hopefully we'll do it all in one shot. All right. It's a little tedious. There's a lot of the examples, though. There's a lot of examples, but we'll cover that for however long it takes. And then that will mean we will have off on Wednesday, right, tentatively. Okay. The packet looks like this. I tried to make an at-a-glance sort of overview of different distributions. This is what section 12.5 is about, different graphs basically that are distribution graphs. Some of this I left some space intentionally because I wanted to have it sort of as a worksheet. All right, the actual information that is, this is what this looks like, this is what this looks like, and so forth is there, but it could always be, sort of annotated. So if you have that, follow along. All right, here's a diagram I had made that is more or less a close-up view of the empirical rule. There's something I want to add to this as well. The physical activity is intended to help you remember. All right. Most importantly, there are 2 tables. This is swiped directly from the textbook. There's 2 halves of tables that you would need in order to answer a lot of these questions. So make sure that you have that. And here is basically an overview instruction of the process, right, of getting from some data information to a probability or to answer some word problem as a percentage. And here are the actual examples. We'll go through each of those. And here is basically the same information swiped from the book. All right, so if you like this a little bit better, you will always have that. All right. This is information about Z-scores and the formula. Right, and this is actually very nice. I couldn't do this any better than it is. This is an instruction of how you would calculate area under a curve given different situations. Okay, so you definitely want to print that. It's part of the more formal portion of this packet. All right, anyhow, let's go through this. There's my glasses here. All right. The first thing I think I should do is give you a quick review of percent equations, because even though that is more fundamental, it might be necessary and perhaps you have forgotten. So here's an example, here's an overview of percent equations. There's 3 types. There's the type that is referred to as the part equation. Then there is something called the base equation. And then there is the actual percentage. This is something the book would take for granted that you know, whether you remember or not. So probably better to take the time up front to make sure that this is all squared away. Okay? Now, of these 3, they come from this 1 sentence long word problem. If you're in the position of teaching little kids especially how to address something, how to solve algebraically, this is a very good segue, a very good place to start, because it starts out as being basically all arithmetic when you're looking for the part that is strictly arithmetic. So what you see is what you get. If it says times, then you're going to multiply and nothing else. These two, all right, are the very inklings of algebra. All right, so these are a little bit more complicated, these two, but they're no more complicated than one-step algebraic equations versus, you know, arithmetic here. Okay. Now, what does an example look like? Basically like this. I'll put it in it's different colors if I can help it. Let's see. A little thought cloud up here. If you had the problem n% of a whole is what? Imagine you had a one sentence wide word problem that was basically this. Such and such percent, and in fact we can just be a little bit more crafty and put a colored N here. That looks nicer. Okay. I purposely put these in green, red, and blue because that is what I have in terms of my color selection of markers. I'm falling apart here. Okay. All right. You'll have imagine a one sentence wide word problem. All right. Such and such, or n as a number percent of a whole, is what? All right. One sentence, and look for the word what. All right. Because it will move around. Basically, the part can be identified as that's the thing that you're looking for. If you see this phrase in context, is what? Right? There's usually a telltale sign that you're looking for this one of the three. Right? If you see in context of what, as if the question moved to the middle, right? Then you're probably looking for this figure, the base, which is essentially a whole. And if it just says what percent, then it's pretty straightforward, right? You know exactly what they're asking. What percent? Right. So look for those phrases, right? If you're trying to figure out which of these three parts you're looking for, three positions, if you will, three figures in the same word problem. All right. Now, as I said, if it were this thing that you were looking for, and the question is what? That's just arithmetic, right? And the arithmetic is multiplication. The word of can translate very easily to multiplication. If you saw out of instead, right, then you might be doing a division problem, right? Out of is usually implying something that is a fraction, right, itself, which is a teeny tiny little division problem. But if you just see the word of, replace that with multiplication x, okay? If you see the word is the equal sign. Okay? That means that whatever is sitting here in the position of the base, namely the whole, that would be here, right? Whatever is sitting here in the position of the part, what, right? That would be here, right? And whatever the percentage is, you could translate into either a fraction or you could make it a decimal. Right? This is, again, I think, having taught little kids to, well, they were 10 is the youngest I've ever taught. If you're teaching elementary school age children, all right, this is a very good way to introduce the concept of algebra, all right, where you have one thing sitting in position for another substituted, a letter, all right, and you just start out with multiplication as an operation, nothing too hairy, all right, and you could teach them how to translate verbal English into mathematical symbols, right, and what to look for, all right. Now, Let me just emphasize one other thing as well, all right? What is the part representative of? This is a portion of the whole, typically, right? The base is, I kind of alluded to already, the whole amount, or you might say the original amount. And this is evidently, right, the percentage. But it's the percent as either a fraction or a decimal, because that's what you need in order to actually use it. Okay? I'm not too complicated, so let me show you the same example from 3 different perspectives, looking for this, and looking for this. And then I'll turn my light on, see if that helps. Is that a little bit better? Hopefully. If you were doing this type of problem, let me partition myself here too. There's a tendency to overwrite. Yeah, need more ruler. Jeez. This is getting pretty dull, this one, so maybe I'll switch. If you had this question, really super easy. 50% of, let's see, 40 is what? Very simple word problem, right? This is what, so you're probably looking for the part of the whole, right? That portion of a whole. And one would assume, given these figures, that it would be a figure that is somewhat smaller than 40. Right? I can't guarantee that that is always the case, because it isn't. Sometimes they can mess with your percentages. All right, but this is usually what you would see, 9 times out of 10. So here, let's take the word of, and we'll translate it to times. We'll take the word is, and translate it to equal, and we'll take the 40 and just drop it in between, because that's where it was in the sentence. All right. And then 50%, you could do it one of 2 ways. Let me get rid of the glare. That's a little bit better, right? You could either make this a half, or 50 over 100 is an equivalent fraction, or 0.50 if you like. So I'm just going to go with what to me is the easiest thing, which is the fraction that a half is equal to, which is a half of 20, right? So if you have, what they're asking essentially, what is half of 20? 50%, pardon me, half of 40. All right, 50% or a half times 40 is literally what? It is 20. That's the part in this particular example, right? Now, if you're looking for this instead, the phrasing of the word problem might change slightly to this. 50% of what is, let's just go with 30. All right. Translate what you can that is consistently true. Of is times, and is equal, and 30 is sitting here. And this 50%, you could, in this context, it might be easy to do it as a decimal, so I'm going to put 0.50. Now, this is an example of an algebraic one-step equation, because the missing chunk here, the thing that you're looking for, is technically referred to as the base. That is in the middle here, so I'm going to put B here for base. All right? So it's technically 0.5 times B equals 30. All right? If you were to rearrange this algebraically, I have no space, so I'm going to write this over here. This is a more concisely written incarnation of this. All right? How do you go about the process? All right? If you're solving for the letter here, which is representative of the base, which is representative of the whole or original amount, you perform opposite operations to manipulate. So the opposite of multiplying by 0.5 is to divide by 0.5. If you've done it here, the balance is to do it here. All right. This is essentially 30 divided by 0.5, which means that what you should get is 60. Right? That's the base in this case, right? 50% of 60 is 30, right? That is, half of 60 is 30, right? You could verify with the calculator or use the fraction of 1/2. If you had 30 over 1/2, then you would have to do 30 divided by 1/2, which is the same as 30 times 2 over 1. Keep, change, flip. Okay? Now in this instance over here, when you're looking for the percentage, let us see really quick. What percent, and they would probably spell it out, of 50 is 25. I'm just making this easy on myself. All right. This is, if you see what percent, it's pretty much the literal percent of these types of percent equations. So what you would do is, again, translate what you can. The word of is times, even if only temporarily, and is equals, and let's see, I want to put it green. 50 is sitting here, so you drop it in between. 25 is sitting here, so you drop it in between. And in this case, because you're looking for the percent, you might use P logically. And again, this is an algebraic equation. It's one step, not too complicated, right? Because again, I'm out of space, I'm going to do the work over here. If you had P essentially times 50, and you were conforming to better etiquette, right? The coefficient would be in the front of the letter, all right? So if I just draw them like this, 50 dot P equals 25, that's a little bit more natural to an algebraic equation, right? All right. Now, in a similar way to what we had done before, if you want to solve for the letter, you would have to perform opposite operations to manipulate, right? That is to isolate the letter. What's the opposite of multiplying by 50? Dividing by 50. So to move this from here to here, I would have to divide by 50 in both cases. There's a cancellation effect as there was before. In this case, it was a decimal of 0.5. And then in this case, it's a whole number 0.5. But you get the same result, right? You divide by 50 of something. All right, now, 25 over 50 is already a fraction. If you want to reduce it, you can, or you could write it in the style of a decimal. All right, the brute force arithmetic involved here would be, if you're dividing 25 by 50, and in the style of a decimal, it might be a little bit easy to convert to a percentage, but that's debatable. 50 would not go into 25, it's too small, so you put 0. 25 goes into 250 exactly how many times? Well, it would be 5, exactly. And then it is 250, and the difference is 0, and you don't need that one, so you have 0.50. This is still looking for a percentage, and what we have here is a decimal. So what you would need as an added step would be to multiply by 100 for the effect of scooting the decimal place over twice, and in which case the percentage would be 50%. Okay? So, why am I bringing this up again? Because it is one incarnation or another of percent equations that might rear its ugly head today. So, this is background information, which again the book takes for granted that you know pretty well. But if you don't, here you have a little reintroduction, if you will, for lack of a better phrase. All right, something to serve as a reminder. My board hath been moved. Okay, so let's see if that makes sense. 50% of 50 is 25. What is half of 50 is essentially the same question. Yes. All right, so again, is what? You're probably looking for the part of what. You're probably looking for the base, which is synonymous with the whole. And what percent is pretty literal, all right? Let's move on to new stuff. there's a diagram that I made for you to summarize a lot, and I'll walk you through maybe adding a little factual information. So basically this sheet, if you happen to have it printed, let's look at this and then annotate. Oh, shoot. Wake up. Let me see how badly this is wolf now. Yeah, not bad. Okay. There is a weird glare. That is the reflection of the actual board itself onto the board itself. Interesting. Alright. I'm interested in this particular diagram. Okay. Yeah. Somebody moved my camera. I think I know who it was. It was the other person who lives here. So let me just try to rectify this. No, that's not good. That's probably as clear as it's gonna get. Alright, good enough. Alright, we're discussing in section 12.5 frequency distributions, which you already have an introduction to. Right? Histograms, right, are a frequency distribution, remember. Right? Each of these is technically a histogram. A glorified bar chart, type of bar chart. But what could be added to them, right, are lines, right, or curves, right, to describe each of these situations, right. Usually you have a lot of data, so the size of the bars is quite narrow, all right, and in which case they're not as pixelated looking, right. Less and less blocky, right, until the point that they are curved. All right, now, what you see here in black, this is the textbook way of referring to each of these things, all right? It would probably be better in the long run, just to be for the sake of politeness, to refer to them in these ways, right? When you see something like this, which to me looks something like a row of houses, right, because it's blocky and they're all basically the same height, it would be technically referred to as a rectangular distribution, okay? These, I feel, are a little bit of a misnomer, not a misnomer, but misleading at the very least. They're called J-shape, right? Now, when you think J-shaped, you may think curved, right? But the definition of them is that they are increasing at a consistent rate, which would imply that there isn't a curve, there is a straight line here, or here, in theory. Anyhow, to me, is a little bit more intuitive to think of them as basically being like stairways, right? So you have a stairway up and a stairway down, right? Remember, we read from left to right, so this is the way you would read it. This is going up, so this is increasing, and this is going down, so this is decreasing, all right? Over here you have bimodal frequency distribution. This, for lack of a more gentler expression to me, it could have been a regular sort of histogram, but instead what you got is that there are two apparent, it would be incorrect to say modes, but you have two frequencies that are distinguished from all of the others. Now the trick here is that these have to be non-adjacent. All right, anyhow, let's think of them as being, if you see something that essentially looks like two middle fingers, all right, that's probably a bimodal frequency distribution. All right, the most famous and most important of all of these is the normal or Gaussian distribution, right? And there's something called the empirical rule that we're going to go into, right, abbreviated here. The empirical rule has to do with percentages of data, all right? And it's basically this where they would reside under this lump, right? Again, if you had a lot of data, then the width of these classes would be quite narrow to the point that it is infinitesimally small. So it would be a curve instead of, you know, a pixelated blocky mountain, right? That's true in any of these cases, really, except perhaps for rectangular. And even then, they might be, you know, just a straight line. Anyhow, two things about this that are important right now. The empirical rule, which we're going to go into again, and that if you're given a normal or Gaussian distribution of data, all right, you can apply something called the Z-score formula, which looks like this, right, which is why I put this in a thought cloud adjacent to this information. All right, anyhow. Think of this as being like a row of houses, so frequency row, if you will. Think of this as being like stairways. All right, think of this as being as like two middle fingers, and think of this as more or less being like a very perfect mountain, you know, your best Bob Ross mountain that you could possibly draw. And then there are these two, the skewed type of histograms, all right? You have those that are technically skewed left, which means that they're a little distorted this way, or skewed right, which means that they're a little distorted this way, all right? To me, the fun way to sort of think about them, or maybe remind yourself, is the way I remind myself, would be to think of them as having a little tail, you know, and I would say a devil tail because they're distorting something. So, you know, they're bedeviling you. So they might be a piece of data or frequency that is stretching the graph out beyond being a perfectly symmetrical mountain. Right? So they're kind of more or less screwing up the picture here and here for you. All right? If the tail is on the left, then they would describe this graph as skewed left. All right? So I kind of just exaggerated and drew a little devil tail here. All right? If the tail of this, that is that data point that is stretching this, all right, is on the very far right, then you might say that the graph is skewed right. Okay? So frequency, row or a row of houses, whatever you like, two middle fingers, stairways to heaven and to hell, all right, a mountain, a perfect Bob Ross mountain, and devil tails, skewed right, skewed left. Now, here's some examples in a little bit more detail. I'll put this in a little bit more obvious colors. Hopefully these will cooperate. And some water. What causes something to be a rectangular frequency distribution? Well, it's when all frequencies occur in about the same amount. There's a lot of leeway in statistics, all right? So they don't have to be perfect, they just have to be, you know, statistically close enough, all right? All right, to be more or less rectangular like this, all right? An example of an experiment that would produce a result like this, rectangular, would be a die roll, all right? How come? Because you know in a die that there are 6 sides of a die, at least the basic die, a standard cubical die. And if you do enough die rolls, all right, the face that is 1, 2, 3, 4, 5, or 6 will occur in the same frequency. right? At least theoretically, one would expect, right, the same frequency, right, for it to be a fair, quote unquote die roll. Right? If you have a situation where you have bimodal, all right, apparently bimodal frequency distribution, right? The condition here is that these are two non-adjacent frequencies. That, although not necessarily equal, and normally we would think that, right? Although not necessarily equal, right, are easily distinguished. From all others. Right? Normally when we think bimodal, that these are two things that occur in the same amount, not a winner and then a runner-up. But in the case of a histogram, it is still referred to that way, as implying as if these were the same height. In reality, they're not, right? They just have to be non-adjacent, because if they were actually adjacent, they'd be a little bit more like the typical histogram. Okay, there has to be an obvious gap in between them. Two middle fingers, really. All right, to exaggerate, I should say. What is an example for something like this? If you had a frequency distribution of weights, the weights of men and women per se, right? Men and women can have the same weight, right? But women tend to be a little bit shorter, not exclusively true, so their weights tend to be a little bit lower than men. All right, anyhow, if you were to superimpose those frequencies in the same graph, all right, you might see an average of women's weights that is distinct from an average of men's weights. Okay? So it would be a bimodal distribution in that regard. Go to sleep. Don't go to sleep. Let's see. I wish this was just a bit sharper. I'm sorry not to obsess over it when we're working here, but I want it to be clear. All right. I don't think that improved it too much. Okay. For J-shaped, or what I like to call stairways instead, right? That's really what would be the case here. You either have an increase right, of frequency or a decrease in frequency, right, at a consistent rate. All right, so what that means, constant or consistent rate, is that this really should be a straight line, right? What is hovering above them to imply the projection here. And notice that it doesn't dip after it reaches a maximum, right? That is why it is distinct from things that are skewed, right? They may seem to be sort of consistently increasing this way, and then there's a drop. But in the case of J-shaped or stairways, right, they don't have that drop off, right? There isn't a ball or frequency immediately after the maximum, right, or immediately after the minimum. Okay. Let's see. What is an example to illustrate this? Well, perhaps a frequency distribution of the number of hours of study in a week. Right, now it depends on the person, of course, but let's just say hypothetically. I'll zoom in on this for just a moment. assume for maybe a second that this is the number of hours on Monday, Tuesday, Wednesday, Thursday, Friday. These bars are days of the week, and that they're really the class of hours, right? But they coincide with the days of the week, all right? And the same thing here. Let's just say that this coincides with Monday, Tuesday, Wednesday, Thursday, Friday, all right? Some people, they start out the week really slow, right? So they're not really that enthused, right? And they don't put in that number of hours. But as the week progresses up to Friday, they sort of get more and more into it, whatever it is that they're doing. Other people, all right, they start out the week with, yeah, I'm going to be the best student ever, right? So I study 20 hours this week and not sleep at all. And then it catches up with them, all right, and they just slowly decline, all right? So they put in a little less effort, a little less effort, a little less effort, a little less effort each day, all right? All right? One is not better than the other. It really is a matter of personal preference, but this is meant to illustrate either a constant rate of increase for frequency or a constant rate of decrease for frequency, okay? Let me just shrink this now. All right, there we are. All right. Let me go over here to skewed, all right, because the meat and potatoes of this entire lesson is really this section here. All right. A situation like this, where you have skewed frequency distributions, is that there might potentially be an outlier. There is a distortion in the histogram. Potentially. Can't say certainly, by an outlier, right? There's a formal definition of an outlier calculation that you would have to perform. That is beyond the scope of this class. You're not expected to do that, all right? But, all right, for right now, think of an outlier as basically being a bad piece of data, right? That is somehow peculiar than the rest. It's drastically different from, the others. So that would cause a distortion. Perhaps you have a very high number in your frequency distribution, or you have a very low number in your frequency distribution. That would cause a distortion if you connected all the dots, all the maximum. All right. Now again, if the tail, bedeviling tail here, is a minimum of some sort, all right, then it would be a skewed left graph, and it would look something like this. All right. Or if you had a maximum that is quite high, quite drastically different, you would have a graph that is skewed right instead, right? What is maybe even more important is just the figures involved themselves. Now, we know that when you have a histogram, that there's different types of averages factored in here, all right? The mean, median, and mode. In a situation like this, all right, where you have skewed left, all right, this would be the order that you would see the mean, the median, and the mode. The mode would have to be the most frequent of all of these. So it would be on the far left. It would be the greatest number, the largest of these three. The mean would be, in theory, a little bit shifted further, all right, to the left. So the mean, the median, and the mode would occur in this order in a skewed left diagram, all right? I'm sorry if that's a little bit hard to see, all right? This information is actually in the packet, so I'll just point to it if it makes it a little bit easier. From the borrowed information. Where is it? There you go. This page, these two diagrams is what I'm discussing here. The mean, the median, and the mode. This is a skewed left diagram, which is ironically on the right side here. Stupid. All right. And in this situation, we have skewed right. Look where the mode would be now. Mode would be naturally the tallest frequency here. So put this in a different color. The mode would be on the very far left. The median would still be in the middle. And the mean would be on the far right. Right? oftentimes you don't even have a picture, you just have the numbers to stare at. If you were given this situation where the mode is the lowest number, the median is in the middle, and the mean is on the far right, all right, you'll probably have it describing this situation where you have a skewed right histogram, frequency distribution. Okay? Right. Notice one thing that is an important lesson about this. When you have these two situations, what is consistently true? The median is always in the middle. So that's probably the most reliable average of these two situations, right? All right. Now, because this is kind of getting to be a bit of a mess here, let me erase some stuff so we get less distracting, and then zero in on this. There are whole pages dedicated to this, but we'll talk about the normal or Gaussian distribution, right? The empirical rule, all right, is applied to when you have a frequency distribution that is either normal or Gaussian, named after a famous mathematician, right? Gauss, all right? Anyhow, the empirical rule is about percentages, right? It's about percentages of the data, where they lie, all right? You would need to understand standard deviation. Remember, standard deviation is a calculation that we had done, all right, in the last section, all right? From here to here, in this lump, that is a curve superimposed over the histogram, is one standard deviation this way and this way. So you might say negative in this context and positive in this context. 68% of the data fits under this part of the lump. 95% of the data goes into two standard deviations, left and right. So a greater percentage, naturally. 99.7% of the data goes to three standard deviations, negative this way, positive this way. All right? That is the empirical rule summarized. It is about the percentages of the data where they would lie under the curve, essentially. All right? Now, let me back off just a wee bit here. What characterizes something as being a normal or Gaussian perfect mountain distribution? There are these characteristics, right? As you can see, the data is basically bell-shaped. This is a bit faint. It's bell-shaped, right? Why is it bell-shaped? It is basically symmetrical, right, about the mean, right? So the very middle here, the average that is here, is the mean, right? In reality, what's interesting about it, compared to when you have skewed data, is that all three averages, mean, median, and mode, they're all the same. The mean is equal to the median, which is equal to the mode, right? In this situation, the ideal situation, right? One is not greater than another or less than another, right? They are in fact the same figure occurring in the same place. Right? And they're all at the center of the lump. Okay. Now, as for examples, this whole chapter is about this. All right. All right. So let's go in. Let me show you another slide that I had prepared to discuss the next logical thing, which is Z-score. Right. Let me get out of here. I'm going to come back to this sheet, which is the same diagram in a moment, but I just want to add one thing to it later. Let's see. Follow this train of thought. Right. What you'll be doing in this section. You'll be given data values which are represented by x, or perhaps the mean, which is x bar, right? Or the standard deviation, which is in this case a lowercase sigma, all right? You're going to use these three figures in tandem or together, all right, to essentially calculate something that is referred to as a z-score. Right? A z-score literally is a ratio, right? Which means it's a what? It's a glorified fraction, right? And fractions can have equivalent fractions. This is very faint. That's getting thrown out. Remember equivalent fractions. Like if you calculated a z-score of 0.5, you could write that as the fraction 1/2. But of course, a fraction could be 5/10, right? It could be 3/6, all right? It could be 7/14. It could be 14/28, so whatever you want, all right? Something that is an equivalent. Anyhow, you use these to calculate this, all right? That is, because it's an equivalent fraction, is essentially proportionate to an area that you will see under the curve, all right, up to the point of the z-score. Okay, now one thing to bear in mind, when you're reading z-scores, they're calculated from the left, the far left, to the right. Right, that will sort of complicate the situation when you're trying to figure something in between two z-scores. Right, but it's not too egregious, really. All right. All right. Anyhow, you read from the far left to up to the z-score. All right. You use these to calculate this because it is proportionate to an area. All right. That decimal number that you get, right, is these are decimal numbers, incidentally. Remember, decimals, percentages, and fractions are three styles of the same figure, potentially. That will correlate to a percentage, right? Which is why I brought up percent equations before. Here you have it again in a little thought balloon. Such and such percent of a whole is a part, right? So if you need to, for whatever reason, perhaps the specifics of some word problem are that you have to calculate what the part is given the percentage, you would use this strategy, right? So, to reiterate, you're going to use these to calculate this, which is proportionate to that, corresponds to this, and, because we are in statistics, that can also be a probability, right? That is the train of thought, right? You're going to use these to calculate this because it is proportionate to that. And then maybe in the end use it to solve for some specific part of a whole, or think about it in terms of a probability, okay? Now, to zoom in a little bit, and you have this again in the textbooks material, which I included, and I'll point to here. Here is the formula for z-score, right? Written in English. The value of a piece of data, right? The mean is x bar, the standard deviation, right? You could calculate a mean, right, given the entire set of data. You can calculate a standard deviation given the entire set of data if you want to. But we're in section 12.5 now, and they'll be less likely to do that, right? Instead, they will give you these figures, all right? And you will insert them in the proper position in this formula. One data value, all right, in respect of the mean, right, would give you one distance, right? To dissect this, remember, what is standard deviation? Standard deviation is essentially an average of distances to and from the mean. So if this is the average, all right, and this is one unique example because this is one unique distance to the mean, all right, one could calculate a z-score, a ratio of that whole, if you will. Being that this is, again, an average, this is generally a larger figure, right? Or it could be, the situation could be reversed. This one unique example that's being analyzed, all right, could exceed this figure, right? In which case you get a number like, 2 point something, or what have you, right? That is really referring to where the data value is in respect of, the mean, right? So in the graph. Sorry, I'm choking here. All right, last thing before we get rolling here. I just want to exaggerate this picture here. All right. Here is a drawing that I had done myself using PowerPoint, right, which is a sort of an expanded view of the empirical rule and a normal distribution lump, right? Again, we're looking for areas, right? So if it helps at all, right, just because it's a larger picture, all right, what we're going to be trying to do is to basically calculate areas under the curve. That is normally the job of a problem in calculus, right? Right. You could use calculus, all right, to calculate area. Integration is a subject of calculus, right? It will give you areas under curves between two locations, right? But we don't need it because what do we have? We have tables that have already done a lot of that work for us, which is why it is really imperative that you have this printout. All right. This is some basically tables of z-scores, right, that have already figured out that average, that area, right, for different scenarios. So you don't need to perform calculus in order to answer any questions here. Thankfully, that is beyond the scope of this class, right? Right? You just need to learn how to refer to this table, right? Z-scores are going to be, as you can see, decimal numbers, right? And on one end, they have it as far as negative 3.5 standard deviations, right? Right, from the mean, right? And on the positive end, the other half of this table, it's 2 pages wide, you'll see that it goes up to positive 3.4, right? A z-score of 3.4 correlates to this area, or, depending upon the degree of precision, right? You go here. All right, if the z-score is greater than 3.49, use one whole as the area, okay? Now, if you look at the very tippy top of these, let's say that you had a z-score of 0.11. 0.11. The precision goes to the hundredths place. Right, so you would go to firstly the tenths place. Tenths is 0.1 here, right? The first digit. And then go over to the column where it has 0.01. So this would be the area that you're looking for. The area that correlates to, or is proportionate to, this z-score. All right? 0.5438, say, for example. All right? Think about what that means. The area that is under this lump entirely is one whole. Entirely, which is why they refer to 3.4 or greater, 3.5 technically, something like that, as being 1.0000. All right, that's the maximum. All right, it's proportionate to an actual area in real life. All right, without using a specific unit, it's a decimal number instead. All right. What is naturally going to happen is that if you don't go all the way to the edge here, from left to right, If you're just somewhere in between, you're not going to be the entire thing, right, in terms of area. You're going to be some portion of the whole that just goes so far, right, which is why you were a decimal that is somewhat smaller, right? If you were exactly a z-score exactly of 0.0, then notice what the area is. It's half. That would be basically an area that goes that far, right? Exactly half area, as opposed to the whole 9 yards, okay? The whole 10 yards. All right, so definitely you want to print out this table because it would spare you from having to perform, calculus to get the equivalent, So I'll get rid of this now, and we'll do some examples. There's a little bit of technique as we go along. Let's start with the more basic type. Erase the mess here. Alright, I think just to spare myself from having to struggle to fit something in a place that won't fit, I'm going to sort of, where I can get away with it, paraphrase what is the actual problem, right, and then just write it myself on my full-size board. Alright, let me read you one to begin with. The heights for females that are the same age are normally distributed. If you see that something is referred to as normally distributed, what does that mean? It means that you could use the z-score formula, right, for all intents and purposes. All right. In a random sample of 500 females, determine the approximate number of females in the sample who are expected to have a height within 1 standard deviation, right? In other words, what's the percentage of people that would fit, within 1% within 1 standard deviation of the mean? Which, remember, the empirical rule, right, is 68%, right? Let me minimize this and turn this off now. To paraphrase, this is example 1 here. Of 500 people, 500 females, right, determine the approximate number A, and here's B over here, within 1 standard deviation. And in the case of B, it's within 2 standard deviations, right? Okay. Now, get in the habit when you're doing any of these problems to draw a simple picture. Draw a lump like this, all right? And label it like that. According to the empirical rule, what is true about the percentages of data? All right, within 1 standard deviation, that is this way or this way, and I'm going to just add to this picture by doing that. 1s, 1s, that's negative and that's positive. 68% of the data would lie in this much of the area. According to the empirical rule, right, if you were to stretch beyond that to 2 standard deviations, this way or this way, right, how much of the data would be represented in that case? 95% would be in this area under the curve. So what they're asking you is to determine a number out of 500. Right? So what are we going to do? We're going to borrow from the percent equations, but we have the two percentages that we need. Right? In this case, because it's within one standard deviation, we're going to use the number 68%. Right? And in this case, we're talking about two standard deviations, we're going to use the number 95%. Right? So to write a very concise, one sentence long percent equation, right, we'll be doing this. We'll be asking 68% of 500 is what in this case? And in this instance, we're going to be 95% of 500 is what? We're looking for the part. Right? We're going to try to translate this to a figure out of 500 as opposed to just a generalization of percentage. All right? Of is multiplication, is equals. Of is multiplication, may not end up that way, well, it depends. Is equals. It depends. It's only if you're applying algebra, and we're not doing that in either of these cases, right? Which you have to divide instead. So, what do we have? We have 68%, which I'm going to write in the style of a fraction, so 68 over 100, just because it will make the arithmetic easier. You could use a decimal, there's no sin in that, but watch the advantage of that. If you write 500 as a fraction, it would be 500 over 1. If you wrote 68% as a fraction, it would be 68 over 100. You can cross-simplify these now. So 100 would cancel here to 1, or reduce to 1, and this would reduce to 5, which means that the arithmetic involved is no worse than 68 times 5. Which is 340 women, or 340 females. They didn't really specify if they were talking about human ladies or not. Right. Okay, so 340 out of 500. All right, in this case, again, all this times is equals. And we have 95%, which again, I'm going to pull the same trick. 95 over 100 is an easier way to write this. And 500, you could put as 500 over 1. For the sake of simplifying, right? Cross-simplify. The figure down here is 2 zeros, it's 100. The common factor is 100. And that would make this 5 up here. So then we just do 95 times 5. 25, carry the 2. 45 plus 2 is 47. This would end up being 475 out of 500, which makes sense, right? That this would increase in terms of percentage, they're proportionate, right? As the percentage gets larger, the amount out of 500 would get larger. So 475 is inching closer to the maximum. Okay. Let's do number 2. Number 2 is just getting your feet wet, calculating z-scores, just to figure out what a z-score would equate to. So we'll do these 4, A, B, C, D. Right. Open up windows. I'm having trouble breathing. A little bit of water. Okay, don't listen to the neighbors now. Whatever trouble they're getting in. For this problem, again, just to paraphrase example 2, we're going to calculate, all right, if given something is normally distributed, again, think of that as being code for use Z-score. And if normally distributed and has these conditions, that the mean is 60 and the standard deviation is 15, we'll calculate for A, B, and C here, and D. This is a data value of 75. This is a data value of 81. This is a data value of 60. And this is a 33. You'll see how the Z-score fluctuates as a decimal. What is the formula that you're going to use in each case? Because it's the same formula. It's going to be the data value subtracted from or by the mean over the standard deviation. I'm purposely using green because it doesn't write well, ironically, because then I could draw on top of it. Okay. Now in this case, all right, what are we going to put in place of the mean in every one of them? 60 is going here in the formula. Right, and the standard deviation of 15 is going down here. Right. And we're going to see how that affects the Z-score. In some cases we're going to get a negative value, in some cases we'll get a positive value. So if 75 goes here, then this is really 15 over 15, right? Since we're subtracting. What is 15 divided by 15? This is a Z-score of 1.000, whatever you like, right? What does that mean? It means that the data value that is used here, 75, is, because it's a positive, is one standard deviation above the mean. So above the middle, right? In terms of a picture, if the standard deviation is, pardon me, if the mean is right smack in the middle, then to be one standard deviation above would be basically from here to here. So right up to that point, 75 would have to be a data value in here, up to there. Right? It's above, so it's positive. Okay. If we use 81, we're going to get a decimal in this case, right? What is the difference of 80 and 60? 20. So one extra would be what? 21 over 15. If this is, let me use a different color just not to confuse it here. If it's really the ratio of 21 over 15, let's maybe simplify the fraction. Divide by 3, this would be 7. Divide by 3, this would be 5. All right. So to get a decimal equivalent, 5 goes into this, let's see, 1 time with 2 left over, 1.4. All right. So you have a Z-score in this case of 1.4. All right. Again, what does that mean? It means that the data value is 1.4 standard deviations above the mean again. Right? So here's your lump, right? And there's the mean. 1.4 would be higher than where the middle is. This is very faint too. Mark is all failing me today. All right. So, all right, is that visible? I think it is, right? 1.4. All right. What about this case? If I substitute 60 for the data value, what's 60 minus 60? 0. All right. What is 0 divided by 15? Well, virtually anything with the exception of 0 itself would be 0. That means, for lack of a better expression, means, that the data value used is 0 standard deviations above or below the mean. And that makes sense, right? Because what was the mean? It's exactly 60. Right? So we're talking about a data value that is right there, right in dead center, right? As opposed to there or there. Right? Now in this case, because you have a smaller magnitude figure subtracted by a larger magnitude figure, look what happens. If this is 33 minus 60, here's blue again. Go back to red, hopefully this writes nicely. What's the difference of 60 and 33? You would get negative 27 in this case. Right? So if you have negative 27 over essentially positive 15, you're going to get a negative no matter what. Right? Because a negative divided by a positive is a negative. Let me see if I can reduce it to make the arithmetic a little bit easier on myself without a calculator. Divide by 3, you get 9 here. Divide by 3, you get 5 here. Right? Exactly 10 would be the whole number 2. Right? So this would be 1 point something. 9 divided by 5 goes into this once, 1.8. So in this case, you get a z-score that is equal to negative 1.8. Now finally we have an instance where we have a negative value, all right? Which means what? It means that the data value is 1.8 standard deviations below the mean, right? So in terms of a picture again, here's the lump, there's the middle, it would be this way by 1.8 in respect of the center. Okay? Negatives mean below, positives mean above. What is the point of that? Well, the point of that is that these decimals, 1.4, 0, negative 1.8, they're proportionate to an area, essentially. So, for the example 3, you'll see what happens now. This is an exercise in reading, basically the z-score reference table. Okay, we're going to do number 3 now. All right, the overview of how to go about it, without listening to me if you'd like to jump ahead, is this page. This is very useful. I swiped this from the book. All right, I've had to calculate the area in different circumstances. Right, and in one case it's pretty straightforward. Right. In this case, it's still quite straightforward. It's just a little bit longer. And then there's situations where you have something in between, all right, or on the left as opposed to the right, on the right side or as opposed to the left side of a z-score, all right? Anyhow, I'm going to do them for you. But you could follow with that if you prefer. That blue is going away. Because it's lousy the way that it writes, and it's sticky too. See if that looks. All right, let's see. Let me just very briefly pull up the train of thought diagram here. If you take a look at this, here's example 3. All right, this is basically the process that we're going to be going through. If we're given a z-score, right, then we won't need to do a calculation. Right? We'll just take that z-score and then look at a table, reference table, the z-score table, to see what the proportionate area would be. Right? When you get into the problem 4 and problem 5, we're going to go the whole 9 yards. Okay? Right, so let me turn this off. We're going to determine the area under the curve. Again, a good strategy for doing this is draw a simple picture every time. And we have several of these, so we'll do A through D again. And I will try to confine myself to such and such amount of space. Okay, so this will be for part A, B, C, and D once again. Okay. In all cases, we are going to determine. That doesn't work very well either. Jeez. Area under the curve. Without calculus, so we're going to use the ZScore table. An area under the curve that is to the left of z equals negative 1.00, right? So you don't really need much. Just draw a very simple picture, right? And remember, here's the lump. To cut it in half, and then maybe just label that the average here, mean, right? If this is 0, right, and it will be, for all of these types of problems, it will be 0, right? Where would negative 1 be in respect of 0? On the left side or on the right side? Well, it would naturally be on the right side. Pardon me, the left. I have the right. Here. So maybe just label that negative 1, right? If we're calculating an area under the curve, what that means is we're calculating the area up to that point. We want to figure out this area, right? There really isn't anything to it. We're just going to read the table for z negative 1, right? All right, that means go to the reference table. It's 2 pages, unfortunately. And look here for negative 1. Here's negative 1.0. The first column is point zeros into infinity, right? So we're going to read that value, which is already highlighted here and circled, right, for the proportionate area, right? In terms of out of one whole, literally 1.000, the amount of area that just goes up to this place, right, is that decimal equivalent, right? 0.1587, looks like. I'm reading it backwards. Yep. All right. So, the area up to here is 0.1587, right? out of 1.0000. Okay? It's a fraction of the whole. All right, the maximum again would be 1. In this case, if you were going to calculate the area under the curve to the left of the z-score that is 1.19, right? Again, draw a simple picture, is it will give you an idea, an inkling as to where the value would be, where you're looking, right? Here's x bar, the average, and again, that's 0 for all intents and purposes. And your figure is positive 1, as opposed to it was negative before. Positive 1.19 in respect of 0 would be to the right of it. So just draw a line like this, right? And if you want to, you could label it 1.19, right? And then scribble, like this much of the area is what we're considering now. The area up to that point. We always read left to right, right? Correct. Okay. So this is, again, an exercise in just using the reference table. So I have to put that down. If you look at, these are all negative z-scores, right? If you turn to the next page, and this is a little bit trickier because we have a hundredths place that is 9/100ths that we have to read for, right? We're going to go to 1.1, positive. 1.1 is right here. And then go over to the column that is 9/100ths, yes. So we're going to go to here, all the way to the end, which is already taken, right? 0.8830, right? Because it is so close to the edge, right? That is why it is a higher decimal proportionately, right? So in this case, the area is 0.883. This corresponds to that area, all right? Out of the maximum of 1.000, right? It's proportionate to that. Almost the whole kit and caboodle, but not quite. Now, when you get a situation like what follows, right, you're going to be asked, at this point, we were reading things that were to the left, right, which is how the table is rigged to begin with. Left, left. And in this instance, what you're going to see to throw things up, we're going to be, switch things up, we're going to be reading the graph to the right of the z-score. So if the z-score in this case for C is the same figure of positive 1.19, we'll have to make a little adjustment. It's still positive. But this is why, again, you would want to draw a simple picture, right? Because it will give you an idea where to look. So you draw a horizontal line, draw a simple lump, draw the center, and understand that this is 0. And then put a line where positive 1.1 would be in respect of 0, which is the same place, 1.19, but read, scribble from the right of that. So we're going to calculate the area that is on the right side here. Right? It's not going to be the same thing. Right? You have two choices basically when you're doing this. You could either subtract the value that we just calculated, 0.8830, from 1.000, right? Because remember, that's the whole, right? This is going up to the point of 0.8830. This would be going all the way to the whole of 1. So if you wanted to figure out the difference, right, that would give you just the area from here to here. What is probably easier than doing that is to consider symmetry, right? consider the symmetry. My neighbors are fighting. All right. Consider symmetry. In other words, look at negative 1.19 on the table, and it will give you the equivalent of having gone through this process. So here's one. This is a little cheap, but it works very well. All right. The area that would be from here to here would have to be the same area from here to here, in theory, right? This would be the same proportionately. Right? It's just from a different part. So, if you go to negative 1.19 on the table, you can just figure out what the decimal is. Here's negative 1.1, and then go over to here, 1170, right? 0.1170. As there is the 9/100ths. All right? So, this is an area is equal to 0.1170. Okay? By just using the table and considering the symmetry, because it would have to be symmetrical if it is truly a normal distribution anyhow, right? All right. Now, if you wanted to, if you took 1 and subtracted what would be the area up to that point, you would use the same figure from before, 88.30. Look what you get as an answer. All right. Here is 1 minus 0.8830 with your calculator. 11.7, it would be 0. Right. There's more than one way to do it. I think using the table is probably the fastest way to do it. Now, when you get to the next example, you really have no choice because it's going to be an area of between instead. So in this case, it's going to be asking you, what is the area between 2 points? Z is equal to negative 1.62 and 2.67. Pardon me, 57. So if you have, again, draw a simple picture. Here's a lump. This is the center, which one would assume is 0 virtually every time. Let us place lines to designate negative 1.62 and positive 2.57, all right, in the appropriate places. All right, I'm going to use red because it shows up nicer. All right, a negative number in respect of 0 would be to the left of it, so I'm just going to draw a simple increment here. Negative 1.62, all right, and then a positive would be to the right of 0, which would be a little bit further along technically, but it doesn't have to be beautiful. All right, so this would be positive 2.57. All right, in this instance, we're trying to calculate the average, the area that is in between these. We want to know this area between, all right, as opposed to the right, as in this weird case, or to the left. The left's easy. The between is a little bit more tricky. It isn't terrible, but here's what you do. All right. This is the technique I would do. All right. The area between, which I'm just going to put as BET, as a subscript, all right, is equal to area that is the larger area minus the area that is technically the smaller area. Now, what do I mean by larger and smaller? Think about, I know that there's a hole here, basically a gap. Think about reading it from left to right. If you were to read the entire thing up to the same point, of these two, right, as opposed to reading it up to, say, this point from here to here, because we always read left to right, which of these technically would be larger, right? If it was starting from here instead and included this gap here, but it went all the way to that edge that coincides with 2.57, I would argue that is the larger area. All right, if you were reading just this much from the same starting point to just that far, negative 1.62, then you have a smaller area. All right, we're going to look at the corresponding areas in the Z-score table, all right, for these Z-scores. All right, and then we're going to subtract them, because if we superimpose one upon the other, all right, we will subtract out that gap, right? And we won't have to worry about it. So let's look at the area for 2.57. We would go here in the table for where it is positive, go down to where it says 2.5, and then go over to the column that is 7, right? Which I want to say is next one, that one, all right? So it should be 0.9949. So this first area here, 0.9949, would be everything including the whole up to that point. I shouldn't say whole because it's not quite accurate, but all right, that much area, region, if you will. This one, that is the smaller one, 1.62, negative 1.62. We have to go to the other point in the graph. So negative 1.6, and this is 0, this is 1, this is 2. Here's the column heading of 200ths. 1.62 would be 0.5, looks like 26. You can read it backwards. 0.526, right? 0.05, I should say. Right. So in this case, it's short on real estate here, 0.0526 and we're subtracting here. Okay. That will give us just the area that is between. All right. Just to make this a little bit more obvious, this is large. And this is the small area. That writes very nicely. And we're subtracting to get the area between. So you take the calculator, right? And you went to 0.9949 minus 0.0526. Sorry for the glare. And it tells you 0.9423. Right? 0.9423 is just this much. All right, there's always a trick, right? All right, just beware. These are your 3 situations. You're either going to be reading from the left, in which case you're just using the table. You're either going to be reading from, or alternatively reading from the right, which you could do subtraction from a whole, or you just can consider symmetry. Look at the negative version of this positive 1.19. All right, and just it will be the same area, 1170. Sounds like an address. All right, and then between, then you definitely have to subtract. Okay. All right, moving on. without having to turn, come on, this is really sleep now. Without having to turn my projector on and off, which is time consuming here. I'm gonna do number 4 now, and this is in 6 parts here, A through F it looks like. All right. And we'll calculate the intelligent, no, I'm not actually doing that. The intelligent quotients, IQ scores are normally distributed, all right? Again, you see normally distributed go, I could use Z-score, okay? With a mean of 100 and a standard deviation of 15. Determine the percent of individuals with scores 115, below 70, between 2 places, and so forth. All right. Because it is a little redundant, all right, what's different about this problem versus the other? Not much, really. But we're going to have to calculate Z-score. All right, so here's that little piece of paper to show you the train of thought here. All right, in this instance, we're going to be given a data value, which is an IQ score, an average, which is 100 for IQ score, and a standard deviation of 15. So we're going to take these to first calculate a Z-score, then use the table to look up the corresponding proportionate area, all right, and then translate that into a percentage. So we're going in 3 steps in this case. All right. So let me just abbreviate here. All right, we're going to take data values, all right, calculate a Z-score, look it up in the table to get an area, and then translate the area to a percentage. All right. That's the train of thought, essentially, in this case. So there's 6 of these. So let me just start with 3 increments this way, giving myself just a wee bit of extra space. All right. So we're looking for, as eventually, the percent. I hope that this is visible. Percent given these conditions. That's not going to work very well. A, B, C to start with. Below 115. Right. Below 130. And C is below 70. All right. Now, the way that they've described the IQ lump is that the average in this case is 100 as opposed to 0. Nonetheless, that's really why we have to calculate a Z-score, because it would be proportionate, it would be an equivalent fraction. All right. Instead of starting at 0, we're going to have it start at, the middle would be 100 rather. All right. Now, let us just isolate, where would 115 be in respect of 100? It's a positive, they're all positive in this cases, but in this case, in respect of 100, 115 would be here. So we're considering basically a percentage / area that goes up to that boundary. Right. In order to accomplish that, we have to calculate a Z-score to get the proportion equivalent. Right. Get an equivalent using these figures, I should say. All right, so if this is the formula for Z-score, all right, what are we doing? We're going to insert $100 here in the formula, the figure that we're talking about, 115 here, and the standard deviation of 15 here. All right, what is the difference of 115 and 100? It is once again 15 over 15. Which is 1.0. All right, this is Z-score. What does that correlate to as an area? you'd have to go to the table where it says 1, 0. I'm getting sick of flipping around. Here's 1, 0, 0.8413. This z-score is an area of 0.8413. Now, this is a decimal in its purest sense, right? How does one translate a decimal into a percentage? In theory, you would multiply it by 100, and the effect is what? It would just simply move the decimal place twice to the right. So scoot this over 2 spaces, and what do you have? You have 84.13%. In the context of this problem, what is that saying? It's saying that people, all right, with an IQ score of 115, or in theory lower than that, that is up to that point, represent 84% of the sample or this population. In this case, it would be a sample, I would assume. All right. Well, maybe not if it's IQ score, right? Anyhow, so 84% of people would be in this area, all right, up to that maximum. Okay. If you did it at 30, it is the same process, just a little bit further along. So here again, you're using 100 as opposed to 0. 130 would be a little bit extra. And we would have to calculate using the z-score formula once again. So z is equal to, in this case, 130 minus 100 over 15. The difference of the 130 and 100 is naturally 30. If you divide 30 by 15, you get exactly 2, right? So, if you look in the table at the corresponding area for 2.0, this z-score represents an area of what? It should be 0.9772. So again, if you're going to translate that into a percentage of the population times 100, the effect is to scoot this decimal over twice, you get 97.72%. Would be from 0 to up to this point. Okay. C is essentially the same thing, but from the other, from the same direction, from left to right, but not going as far. 70 would be where in respect of 100 in this case. Over here. So this would be a smaller area. All right. If you calculated a z-score in this case, it would be 70 minus 100 over 15. In which case you would get what? You get a negative 30 over 15, which means you get a negative 2 in this case. All right. And negative 2 in terms of an area would represent this much. The area would be 0.0228. Right? Times 100 to make it a percentage would be 2.28%. Okay. The problems that follow are, since these are left below, right? All of these that are below a certain number is just reading from the left, which is how the table is rigged. All right. The things that you will see now are perhaps between or above, which would be reading it from the right, technically. So let me do that. case. Problem D would be between 70 and 115. And E would be between something else. Between 115 and 120, it looks like. 130 rather, sorry. And then F is above 130. No, 122. Okay. Remember, when you have to calculate these between figures, you're going to have to subtract. Right? You really have no choice. When you have these above types of problems, you could subtract from the maximum of 1.0, or just consider the symmetry of the negative, which is probably easier, right? In any case, because of the figures that they're giving you, you have to use the Z-score formula. So, in this case, if you're using, and you're doing it twice, right? You're going to use 70 minus 100 over 15. And then in this case, you're going to do 115 minus 100 over 15. And see if you can spare yourself any bit of trouble. You had done the figure for 115 already, all right? And did we do 70? We did 70 as well. So as far as the areas are concerned, well, let me show you these decimals first. This Z-score of would end up being -2, right? Because this is -30, -2. And that correlates to an area of 70 for 70. I'm putting it as a subscript here. Which is what? 0.0228. We just calculated that. This one would be a Z-score of 1, so positive 1.0. And that correlates to an area for 115, which is what? 0.8413. I really should draw the table just to illustrate, so I'll put it here just because I don't have a lot of space. All right, here's the lump. Here's the center of 100. All right, here would be 70 in respect of 100. This is 100, I swear. All right, and here would be 115. And we're trying to calculate the area in between these. So from that minimum to that maximum. All right. We use these Z-scores from the Z-score formula to calculate these areas, respectively. Because we're trying to figure out, all right, what would be just the area in between this minimum and this maximum, we might do a calculation that is basically a larger area. That's pretending for a moment that we're including this gap here, and then a smaller area. Right. So the area between is equal to the area of the larger area minus the area that is the smaller area. Right. We already calculated it, so it's 0.8413. Minus 0.0228, and what you should get in this case is that the area between is equal to what? Where is it? 0.8185. 8185. Save that. Because we still have to translate it to a percentage, but let's just verify if these digits are correct. 0.8413 minus 0.0228. All right. Indeed, sorry for the glare again. If we use this area, the larger area, minus the small area, we get the difference. That is just the space in between. And we get 0.8185. Right? Now, since we are asking about a percentage, though, right, what is this in the style of a percent? Well, multiplying that by 100 just has the effect of moving the decimal place twice. So what is being said here is that in terms of IQ, 81.85% of people would be between this figure and this figure in terms of an IQ. 70 to 115, which is the majority of people, clearly. I encroached upon this one. If you were going to do 115 and 130, it is the same calculation, all right, but using different figures, all right? That is, you calculate a z-score, then you figure out what the areas are from the table, and then you subtract the areas, right, to figure out this problem. So, without reinventing the wheel, humor me a minute and I'll just erase a bit. All right, what you should get in this case is this. I'll draw it really quickly. Is your average of 100. 115 would be a bit higher up, right? And 130 would be a bit higher up. So in this case, you're still calculating an area between, but they're past 100. It isn't really going to change anything in terms of the instruction. You're going to take the z-score, right, translate it into an area, the z-score of 115, using 115, an area of 115. Then you're going to get a z-score using 130, and then you'll look for the area that is 130, right? And then you will take these things in tandem to get the area between. You're going to subtract what in theory would be a larger area. A larger area would be running all the way from the left up to this barrier here. That is, so it goes to 130. And then this slightly smaller area, which would be up to just that barrier there. Right? If you subtract the larger by the smaller, what you'll get are these figures. Right. This area, 0.8413 again, because it's 115. And then for 130, it's 0.9772. We already did that one as well. 0.927. Alright. And what you should get is this difference. 0.1359, which again, you have to convert to make it a percentage. Right, so times 100 to change the style of it, it would be 13.59% for this problem. Right. This one is, again, the one that you could subtract from a whole as opposed to something that is remarkably close to a whole but isn't quite the whole way. All right, or you could use symmetry, all right, which is probably faster, right? I don't want to corrupt your opinion. I just think that that's more efficient, all right? So here's what the picture would look like in this case. Your average is 100, 122.5, which is something that we hadn't calculated at all. In respect of 100 would be here, all right? But they're saying above, which means from the right. We're calculating that much area. Right? so we would have to do brute force here. The z-score would be 122.5 minus 100 over 15. And what do we get? The difference of 122.5 and 100 is 22.5 naturally. If you divide if you divide 22.5 by 15, what do you get? You get 1.5. Now, that's a positive score because of the larger figure in comparison to the mean of 100. If we want to spare ourselves having to subtract, what we can do is just look at the table for the equivalent of negative 1.5 because it will produce the same area. So if we go to the table of negative 1.5, it's 0.668 it looks like. Yep. The negative, which would have to be symmetrical to the positive, would be 0.0668. And then again, if you just want to convert this to answer the question of percentage, you're going to multiply by 100. The effect is to scoot this over twice. You get 6.68%. Right? And you spare yourself a little bit of trouble. Okay. One more of these and then we'll stop. If you look at example 5, it's no worse than what we just done. It's just that they're using alternative phrases in English. So I'm going to be looking at 5 here for a moment. Right? I don't know if I really feel up to doing all of these right now. Right? I'm a little under the weather. Let me make sure that this is clear. All right. To paraphrase, example 5 is the length of time on horseback being normally distributed. Which means what? It means you could use z-score. And then they give you some basic figures here that the mean time would be 3.2 hours. It's the average, right? And the standard deviation would be a fraction of an hour, so 0.4 hours. Notice the units are the same. All right. The context in which you're being asked this, I'll maybe just cut this up into 2 so I have a lot more space. For part A is essentially this. What percent of rides are at least 3.2 hours? Right. This phrase in English, which is at least, can be translated into greater than or equal to. Right. Which means that if you translated that into a lump, right? If I did a simple picture, and this is really why I'm belaboring it, the average in this case is 3.2. So I'm going to put the number 3.2 here, right? Hours. Right. If we're talking about at least, that means, again, greater than this point, which would be expanding it this way, or exactly that point. If this coincidentally happens to be the average, so it's the dead center, that represents what percentage of this picture without doing any calculations? Right. This is half of the graph, right? Because of the coincidence of these figures, 3.2, 3.2. So, and again, why this side, the right side? Because it's at least, which means it's greater than that. Right? Equal would be this line. Half of a graph is how much? It's 50%, right? Without doing a calculation, so the answer is 50. Right? If you answer question B here, the question is, what percent of rides are less than 2.8 hours? All right, remember, what does that translate to from English into math? Less than is that. So in terms of a picture, and again, get in the habit of drawing these lumps because it will make your life a lot easier. 3.2 is the mean in this case, so that's dead center, all right? Where would 2.8 be in respect of 3.2, on the left side or on the right side? It would be, just considering this number and this number, it would be over here somewhere, whatever, all right, 2.8. Now in terms of an area, we're going to refer to this less than, right? Less than means not including this, but just up to it. All right, so we're going to consider the area that is basically up to that point, just short of it. All right, which is the same type of problem that we had been doing. We're just going to have to translate it to a percentage. All right. Again, what is the train of thought in this case? We are going, once again, if I can just separate the pages would be great. I lose my dexterity after a while, because of the mark of dust. But I want to complete this thought, so can you give me a moment? What is it? We're going to follow this train of thought once again, all right? We're going to take the values that they've given us, 2.8, 3.2, and the standard deviation of 0.4, use these to calculate a z-score so that we get something that is equivalent using these figures, all right? Then look up the proportionate area, all right? And then translate that into a percentage to answer this question. So, I need a little bit of space, so I'll erase this. All right. And what do we get? All right, the z-score in this case is x minus x over that. Okay. So if we put in 2.8 here, and we subtract it from the average of 3.2, we're going to naturally get negative, which means that we're going to get and this I'm forgetting is 0.4. You're going to get negative 1.0 as a z-score, right? If we look up the area that corresponds to that, right, the area of negative 1.0, all right, we'd get this decimal, right? 0.1587, and if we multiply by 100 to make it a percentage, that's the effect, 15.87%. Almost 16% of rides are less than 2.8. C is the same idea as A, all right, but the way that it works out is like this. they're asking what percent of rides are at least, again, 3.7 hours. Right, this is greater than or equal to that. So if you drew a lump, and 3.2 would be here, 3.7 in respect to 3.2 would have to be somewhere over here, 3.7. Right? If it is equal to that, it would be right there. Right? If it would be greater than that, which it's ironic that the word least is implying something greater, but in this context, and this is why English is sucky, all right, sometimes, all right, at least is implying greater. You'd have an area that stretches this way. This implies greater. So this is essentially a problem that is from the right, again, as opposed to from the left. So we're going to try symmetry in this case. All right. We're going to calculate a z-score based upon these figures. So z is equal to 3.7 minus 3.2 over 0.4. And the z-score in this context would be 1.25. Right? And that will give us an area of 1.25. We'll have to consider the negative for 1.25 to get that. Wait a minute. I'm doing something backwards. I'm a little stupid right now. Yes, okay, it's fine. Because we're trying to measure from here, rather up to that point, we're going to consider the negative version of this from the table. Symmetry. All right, which means, go to the table, let's see, negative 1.25 is negative 1.2. This is 0 in the hundredths place. This is 1 in the hundredths place. This is 2, 3, 4, 5. 0.1056 it looks like. Yep, 1056. Okay. So this produces an area of 0.1056. Right, which again, if you multiply it by 100, has the effect of moving the decimal place twice, which means that this is 10.56%. Okay. All right, D is a situation where you have data between. So this one is written as what percent of rides between 2.8 and 4.0 hours. And here's the graph, just to illustrate. The center is 3.2 in this context. 2.8 would be lower than this, so it would be a point here. And 4.0 would be higher than this, so it would be a point here. And we will calculate the area in between then. All right, this is the most involved because again, you're going to have to figure out the z-score using 2.8, calculate a z-score using 4.0, and then see what the areas are. All right, and then we're going to subtract them. The area between would essentially be the area that is the larger area, which would be the 4.0 area, minus the area that is the smaller area, which would be the 2.8 area, decimal, decimal, and then convert that to a percentage. That's basically the strategy here. Right. If you were to calculate a z-score in this case, it would be 2.8 minus 3.2 over 0.4. If you calculate a z-score in this case, it would be 4.0 minus 3.2 over 0.4. For this one, because you have a smaller figure, something that is less than the mean, all right, you're going to get a negative. All right, turns out that this is equal to negative 1.0. Right. We look at the area that is technically for negative 1.0. It came from the point of 2.8 naturally. And you get this area. 0. Let's see. 1587. In this case, you get a positive. This turns out to be exactly positive 2. And that's z-score. So we're going to look up the area from point 2, really. It stemmed from 4. Right? And this area is much greater, significantly closer to 1, which is 0.9772 again. All right, and then we subtract them. All right. So 0.9772 minus 0.1587 would produce this. It should be 0.8185, which if we multiply by 100, again has the effect of scooting this decimal over to here, and you get 81.85%. 81, almost 82% of rides are between 2.8 and 4.0 hours. Okay. The last thing is part E. We'll be on time, a little bit over. This question is phrased basically like this for E. Same example, but it's part E. In a random sample of 500 rides, right, how many last at least 3.7 hours. All right, now we had, for the problems that preceded this, it was all percentages. In this case, they want to know how many exactly out of 500. Right? So eventually what's going to happen is we're going to be translating this into whatever percent of 500 is what? Is really what the question is. Right? Now, as for the percentage, we technically already calculated it. All right. Let's see. Part C. Right. We had gotten to answer this question at least, right, which means greater than or equal to. Right. Right. In terms of a graph, here is 3.2. Here is 3.7. And we calculated the area that is at least, which technically means that way, greater, 3.7 or greater, starting from here, right, via symmetry, right? And what we calculated was that the percentage was 10.56%, right, for rides that last at least 3.7 hours. So in our model from percent equations, we're going to insert 10.57% of what 500 people, unique to this problem, is what? All right? We have just a straight arithmetic problem. It's going to be the decimal equivalent of this is 0.1057, right? You could figure out what the fraction is, but the decimal is probably easier in this particular example. Let me get rid of this data. So 10.50 of is times 500 is equals. All right? Enter that figure times that figure. All right? 0.1056 times 500 is 52.8. It should be 0.8. So round it up. If we're talking about approximately, this is about equal to 53 rides. About 53 rides out of 500 are at least 3.7 hours. Right. Okay. Good. And that is that. So, since we covered the whole thing, there won't be a video on Wednesday. It won't be necessary. So I might not see you again. I mean, I'll try to, just be conscientious and talk to you if necessary. All right. But no video on Wednesday. For homework, work on section 12.5. Say, is it 5? It is 5. 12.5 in my lab. All right. If it happens, I forget offhand. It might be part 2 and part 2. Something like that. All right. No video on Wednesday. All right. Because we covered the whole section. We did 12.5. Okay. And then I will not see you again in theory until next Monday. Okay? All right. Thank you guys for sticking with me. I'll see you again next week, if not sooner. All right? But no video on Wednesday, okay? Be careful out there.